Hello everyone, welcome to this NPTEL Structural Geology course. This course is being offered for the undergraduate student and designed accordingly. The first two lectures will cover the introduction, and then slowly we will jump into the other topics of this subject. Before going into the actual course, we'll have some administrative parameters that we will follow in this lecture, and then we'll proceed. So before we start, I'm your instructor. My name is Shantanu Misra. I'm a faculty member in the Department of Earth Sciences of IIT Kanpur. About my academic background, I studied geology in Jadavpur University. I had my bachelor degree, master degree, and also PhD degree from Jadavpur University. Then I moved to ETH Zurich in Switzerland for a postdoc. Later I became a lecturer in the same institute. I learned mostly experimental rock deformation and worked on high pressure temperature deformation behavior of rocks. Then I moved to another beautiful country called New Zealand. The institute was GNS Science. I worked there on earthquakes and landslides phenomena. In 2015, I decided to come back to India and joined IIT Kanpur as a faculty member. My research interest mostly includes primarily experimental rock deformation, rock physics, structural geology, and tectonics. Throughout this course or even later, you can contact me via this email. You also can call me during the office time, and to know more about my research group, and other activities, you can follow me via my web page. Saqib and Manav, these two are the TAs of this course. They are teaching assistants. Both of them are my PhD students. They are CSIR senior research fellows in IIT Kanpur. Saqib joined in 2015, and Manav as well. Saqib works on petrology and structure of Nagaland ophiolite sequences, and Manav works in the direction of rock physics, and he works on enhanced coal bed methane recovery via CO2 sequestration. About the study materials for this course, there are n number of books, there are n number of online resources that you can explore. I particularly recommend these 4 books and few online materials which will be helpful for this course, and I also derived most of the study materials from these 4 books and these online materials. The first book is a book of structural geology, fundamentals and modern developments, written by Professor S.K. Ghosh, who was a professor in Jadavpur University, Kolkata. This book is a little bit of advanced level for an undergraduate student, but initial sections are written in a very general way, in a very scientific way, so that one can understand. What I like about this book, particularly for the students of India, that the examples of geological structures are cited from Indian continents or different Indian fields. So therefore, if you go to the field, you can see those structures and relate yourself. The second and third book are the 2 classic ones. The second book is Structural Geology, which is a second edition of Tuis and Morse. It covers entire span of structural geology, and the third one of Professor John Ramsay, Folding and Fracturing of Rocks, is the classic textbook of structural geology ever considered. It is very important to have this book in your library, and it is a worth reading book. 4 books is relatively new in the structural geology field, written by Professor Foysen. What I like about this book is it's written with the examples of a lot of applications. The language is very easy to comprehend and understand, and most importantly, this book has fantastic field photographs, colored field photographs, and in addition to this, a complementary series of illustrations which are essentially helpful to understand different structural features. About online materials, I recommend these 3. So the first one is a textbook in PDF by Professor Ray Patrice. The second one is a lecture note from Professor John Pierre Burg, and the third one is one YouTube lecture series given by Professor Jana Sorai of Aachen in Germany. In all these three materials, you will get excellent illustrations, very nice texts, and particularly for Professor Urai's lecture, he has given lots of analog models and numerical exercises which will be helpful for you. Needless to mention, there are series of online materials which are available. You just have to type online that what you are looking for. You just type the keywords or the phrase or the sentences, and you will get series of suggestions from Google or whatever search engine you use, and you can figure out what you are looking for. I'm sure you will get it. If not, you are always welcome to contact me or the two teaching assistants of this course. This is the course template of this or course outline of this structural geology course. The course is designed mostly following the general undergraduate courses that is being followed in India and globally. So it's a 12 weeks course. Initially we learn, at least in this lecture and in the next lecture, the introduction and basic concepts of structural geology. Then we'll follow the certain different aspects sequentially one after another to cover different structural elements, their measurements, stereographic projection. We'll learn about strain and stress. We'll learn about rheology and deformation mechanism of rocks. Then slowly we'll go to the actual real rock structures that we see in the field, like foliation and lineation, different types of folds, their formation mechanisms, superposition of folds, then boudinage and related structures, fractures, joints, everything. Then we move to the ductile domain, that's the ductile shear zone, which is very important in structural geology and in general. And finally, we'll end up with some notes on structural mapping, summarize this course, and do some discussions for the future developments and studies. The question that one should ask at the very beginning, that why I should study structural geology. Personally, I like this subject very much. We'll see in course that this subject makes you like a detective. Like you have something in your hand, this is a puzzle, you have no clue what happened in the past. So your challenge or your task is to, whatever you have in your hand, just looking at it, observing it, analyzing it, you have to go and understand what has happened in the past. So in a way, this is a very challenging work and I like it very much. Apart from this, you of course would like to ask that what are the job opportunities, what are the different aspects, that what is my use of studying structural geology in the context of more present day society? The answer is it's significant. So if you are a structural geologist, your demand is in many industries and also certainly in academia. So you can be recruited or you can be hired if you are good enough in exploration and mining industries. You can be also hired in lithostructural mapping and survey companies, construction, engineering, and structural analysis of different surface and subsurface materials. If you are interested to that, there are many industries who are involved in this type of work, and they will certainly would be interested to hire you. For natural hazard analysis, earthquakes, landslides, and so on, your job is secured if you are good at it. Hydrogeology is also one of the areas where structural geologists are in high demand. And apart from this, you can certainly join in academia and petroleum industry and other places where you can work on science and technology development. As I said, that structural geology is a subject that unravels the past of the earth, the history of the earth in a certain way. And there is no clear picture of that. We have to figure out things what we have today in our hands. So these three terms, predictions, uncertainties, and risks, are somehow very much associated with this subject. Whatever you do, you should have some sort of prediction, some sort of risk, and some sort of uncertainty in your discussions and in your results. So always keep this in mind. Okay, so what is structural geology? Now, if you have heard this term before, then you must have heard also these two terms that are being always said or always used together with structural geology. One is tectonics and another is geodynamics. Now, these three terms, structural geology, tectonics and geodynamics, their origin comes from Latin and Greek languages. So, structure comes from the Latin word struere, that means build. Tektos is a Greek word from which we have this word tectonics, that means builder. And then dunamis is a Greek word which means power or force. So, you can see that if these three terms, structural geology, tectonics and geodynamics, well, geology is gi, that means the earth, it is also a Greek word. So, these three terms, as I was talking about, structural geology, tectonics and geodynamics, these three, from their origin of these three words, can suggest you that with the help of or with this action of power and force, how you can build something and who is the builder for that. So, the structural geology is certainly all about power, forces, building something, and if you apply power and force, you have to deform, you have to move something from one point to another. So, scientifically you can finally conclude that the subject structural geology together with tectonics and geodynamics concerns in general with the shape, that is geometry, the displacements, which is kinematics, and forces, so mechanics in our earth and other planetary bodies. Now, interestingly, if you have these terms geometry, kinematics and mechanics, you can certainly comprehend the fact that the subject is highly interdisciplinary, and it is indeed. We take assistance, help and collaborate actively with people from material science, mechanical engineering, physicists, computer science and remote sensing. Within the broader umbrella of earth sciences, we also collaborate with geophysicists, petrologists, igneous, metamorphic and sedimentary domains. We also take active help from survey people, and of course, nowadays we are also taking people from geodesy on board. So, this interdisciplinary nature of this subject makes it highly broad, and in overall geology it makes it a complete science topic together with physics, chemistry, maths and biology. Now, these three subjects or which are commonly used together, structural geology, tectonics and geodynamics, these three form a very coherent and interdependent subdisciplines of geology, and together with these three topics we try to understand that how these rocks, the different rock formations and earth systems in general, crust, lithosphere, asthenosphere, so on, deform, and how do they deform, via which processes. You can understand when you see a rock which is deformed. We'll learn in this lecture how to look at a deformed rock. It contains a lot of information. A piece of rock gives you a series of information. Your idea, or as a structural geologist or a geologist in general, your aim is to unravel this information and use this information to study different processes that happened at the past in the earth, and also what could happen in future. So, let us talk about these three topics: structural geology, tectonics and geodynamics, what these are, whether these are different, whether they are similar, or if there is any difference, then where is the difference. Well, these individual topics, structural geology, tectonics and geodynamics, from science point of view, from approach point of view, they are very similar. Three of these subjects essentially deals with displacement, forces and kinematics, the geometry, shape, etc., etc. But the fundamental difference between these two topics are the scales of observation. So structural geology generally we study in field-based, it's a field-based discipline, and it operates from very micro scale, about 100 microns or less, to 100 meters or maximum 1 or 2 kilometers. So you can say that from a grain to outcrop, if you study rocks, then you are doing structural geology, of course in the context of deformation. The tools that are used to study structural geology include field study, that's very important, rock deformation experiments, you can do analog experiments, and essentially numerical models. In contrary, tectonics is certainly a large scale. As you can see, the entire plate tectonics discipline is pretty large, but it doesn't involve what is happening at the bottom of these plates. It just deals with the movement of the plates, their mutual interactions, and so on. So tectonics in general deals from about 100 meters to 1,000 kilometers in scale. In structural geology, we learned that it is below 100 meters. So tectonics is certainly a large scale study of structural geology, you can consider it this way. The tools we use here are again field study, you can do field work, you can do analog experiments, and you can do numerical models. Geodynamics is a subject that discusses about the forces and processes that drive the plate tectonics and the deformation of the materials inside the earth. So you can consider the mantle convections, plumes, etc., etc. So as you can imagine, the scale from the plate tectonics to where the plates are to the core of the earth or at the core mantle boundary, the scale is huge. So it operates at the scale more than 100 kilometers, and there is no way you can do field work at core mantle boundary or even crust mantle boundary. So there is no scope of doing field work. So what tools we are left with are analog experiments and numerical models. Now to study structural geology, as I was talking about, even for within the subject of structural geology, apart from tectonics and geodynamics, scale is something that is very important, that you always have to remember, or you always have to take into account what is the scale you are looking at, what is the scale of observation. And structural geologists do it very frequently. They jump from one scale to another. Looking at a single grain, the deformation of the single grain, one structural geologist can immediately interpret an entire mountain building process. So this is a fun, this is a skill as well. Apart from the scale, there are three pairs of terms. One is continuous versus discontinuous, second one is homogeneous versus heterogeneous, and third one is isotropic versus anisotropic. We are all familiar with these terms, but let's have a look these 6 terminologies in the context of studying structural geology. For the scales, we generally cover 3 different terms: microscopic, mesoscopic, and megascopic. As the name suggests, microscopic is something that you observe under microscope, be it optical microscope or electron microscope, and we call it microscopic scale. Mesoscopic scale is something that you can cover just by a view. So it is scale that to structure that can be observed without the aid of the microscopes on a hand specimen or a single outcrop and so on. So it's about 1000 meters or 1 kilometers or something like that, and we call it outcrop scale or outcrop study. And then macroscopic scale is something that you're doing a large scale field study or regional scale field observations. So this is greater than 1 kilometer and so on. So it's to be completely exposed in the outcrop that you may not get in the field. You may get something here, something there, in between there is no rock exposure. So it's your background, it's your intellectual quality of the structural geology background, that how you can correlate from this outcrop to that outcrop. And when you do that, you are actually doing a macroscopic field observation or macroscopic study, macroscopic scale study of structural geology. So here is an example of what do we understand by scale. What I try to convey with this slide, you have learned probably already that if a layer is horizontal or at any orientation, and if there is a layer parallel compression, this layer is ductile enough, then it makes a curved feature which is known as fold. Now in these three images, in the first one you can see that the width of the image from the scale is given is about 750 microns. In this 750 microns from here to here approximately, what you see, this green material is an aggregate of biotite mineral, which is a kind of mica. And you can see this biotite is not straight here, it is folded. So there must be a layer parallel compression here. Now if I jump to the next image, we see a very similar structure which is fold, but here the scale is, or this distance in this entire image is close to 50 meters. And if we look at here, this distance is about 4 kilometer, and we almost see a very similar structure. Now if I see fold in the first image and if I see fold in the second or last image, then they characteristically may be same. Mechanically they may be developed in a very similar way, but their scales are different. So therefore, as I was talking about, the concept of scale is very important in structural geology, and one has to jump from one scale to another scale to solve the geometrical problems that we see in the field and also in the experiments and when you do observations under microscope. Now about the continuity and discontinuity of structures, this is something that is also scale dependent. So for example, this picture here, you can understand that this is a layered rock. We are not going into the fact that how did it form and what it is, but we can figure out certainly that it has alternate dark and white colored bands. Now if I follow any of these bands, I see in this scale of observation of this photograph I am looking at, these layers are continuous, that is, there is no discontinuity. However, when this layer got extended and it formed a structure called budinage, we can figure out that few of these layers are continuous here. For example, if I try to draw it here, but there are few layers. For example, if I take this little packet of layers, it comes here, then it vanishes, and then it starts again from somewhere here. So there is certainly a discontinuity. Now this is something what we call continuity and discontinuity, or continuous and discontinuous. We have few more examples, and here we would like to highlight the fact that why this continuity and discontinuity are also scale dependent. For example, here in the first image we see this is a shear zone, ductile shear zone, and this black layer is continuous. However, if I consider this white layer in the second image, it is going like this, and then we have some other material inside, and then probably it continues somewhere here. Now looking at it, I have a discontinuity from here to here, the layer is not continuous. So this is a discontinuity. Here in this image we see again a layered rock, and we have n number of fractures which made these layers discontinuous. Now at this scale of observation I see them as a discontinuous layer, any individual layer, but if I look it from far, I may not see these fractures and I may consider this as a continuous feature. So therefore, continuity and discontinuity in rocks are essentially a function of the scale you are looking at. Again, you have another example where I try to provide, for example, here this is a little complex structure. To understand it better or to highlight its features, I made a sketch of this which is on the right side, and you can see that few layers which are marked by this arrowhead are continuous, and few layers here, these are getting discontinued. And also the entire outcrop or entire image that we can see a little discontinuous line here that is separating by a sleep. So there are many ways you can produce discontinuity, and that is also important to understand that what is the reason for the discontinuity in the structure you are looking at. Coming back to two other terms, that is homogeneous, heterogeneous, isotropy and anisotropy. Now these are very classic terms which are being used in almost all subjects. So in brief, homogeneous materials are of uniform composition throughout, or any properties that you are looking which has uniform properties throughout the material, and if that does not hold, then this is heterogeneous material. Isotropic material is, on the other hand, is one which is the physical properties are equal in all directions, and if that does not happen, then it is anisotropic materials. You can also consider it in a way that material properties are independent of the direction in which they are measured. We will learn more about it with time, but again I would like to remind you the fact that this concept of homogeneity, heterogeneity, isotropy and anisotropy are again function of the scale. So let us have a look on some examples. On the left side we have a photograph of a sandstone, a hand specimen of a sandstone. This is the scale. So if this is 10 centimeters, then maybe this would be around 80 or 90 centimeters altogether. And we see here, if we look at the color, that is one of the physical properties, then color is mostly homogeneous, it does not vary. The appearance is mostly homogeneous, it does not vary. And if we have some tools, if we can measure some other properties like electrical conductivity of rocks, hydraulic conductivity and so on, then we might find that this material is very much homogeneous. And if I make a thin section of this little rock and then I observe it in this scale, then I figure out that it is not at all a homogeneous material. So same piece of rock, I am looking at two different scales, one is homogeneous, another is heterogeneous. About this isotropy and anisotropy, these two are the photographs of two granite hand specimens. The first one is sort of a massive granite. You can see many different scales, but statistically if I consider this entire specimen, then does not matter if I am measuring a property from here to here, that is in two different directions, they would appear more or less same. However, in this sample, if I try to measure a property from here to here, then I actually encounter different layers. However, if I measure from here to here, the properties would remain same because I am following a same material. With time we will know this is known as transverse isotropic material, which is a layered material, and most of the cases our rocks are so. So again the concept of isotropy and anisotropy could be something that you are considering with respect to the scale. So we are almost at the conclusion of this lecture, and what we learned from this lecture is very important when you see or when you go to the field or when you see a photograph of a rock sample. The first question you should ask as a structural geologist, am I looking at a deformed rock? And if yes, then what is the scale of the structure I am looking at? If this rock deformation or different layers or different features that I am looking at are homogeneous or heterogeneous, and if this rock is isotropic and or anisotropic. So with this note, I conclude this lecture, and in the next lecture we will mostly learn what are the different ways structural geologists approach to look at deformed rocks. Thank you very much and stay tuned.